Good evening, everybody, and welcome to tonight's event from the Jesus College Intellectual Forum. So tonight I'm delighted to welcome Professor Derek Smith to tell us everything we want to know about COVID-19 mutations, what they mean for vaccination strategies. Derek is the Professor of Infectious Disease Informatics in the Zoology Department here at Cambridge, and also advises the World Health Organization on many things, including how to choose the annual flu vaccines that many of us get each time. I should warn you that Derek is not a medical doctor. So if your questions are really those that you should address to your own doctor, they're probably not the ideal ones to ask Derek tonight. And if you want to ask about WHO strategy, then in just a few weeks, we have Peter Singer, who's special advisor to Dr. Tedros, who runs the WHO, to talk about vaccine nationalization and the World Health Organization's role. So you may well want to come to that and have some questions there. But tonight, I'm delighted to welcome Derek. Derek, over to you.
Thank you very much, Julian. It's really a pleasure to be here. It's normal when one gives scientific talks these days to say at the beginning whether one has any conflicts of interest. So I'm going to do that. I don't have any conflicts of interest. I've never worked for a pharmaceutical company. I've never had any grants from a pharmaceutical company or done any consulting with a pharmaceutical company or any other for-profit organization. I do, as Julian said, do a lot of work with the World Health Organization, but I'm speaking today not on behalf of the WHO, but as an academic here in Cambridge and our own work and what I know of others' work on COVID-19. I'm a member of some of the UK SAGE subcommittees on flu vaccine, on COVID vaccines and updating COVID vaccines. But again, I'm not speaking for SAGE today, but as me. Yeah, so that's it in terms of conflicts of interest. Thank you, Julian, for that introduction. And Julian, of course, says, somewhat ironically, that I will tell you everything that we want to know about COVID-19 mutations, because he knows very well, as I do, that nobody knows enough yet about these mutations. And when Julian invited me a couple of months ago to give this talk, one of the things that we said then is, look, we really don't know how much we will know 2 months from now to talk about this, of course. But I think we're actually in a really nice sweet spot to talk about this, because if everything were known about these mutations, there would be no interest for you to come to this talk. You could read it in your favorite newspaper, listen to it from your favorite chief medical officer or scientific officer or prime minister. And if there were very little known, there would really be very little to say other than there's a lot of work to do. But there's enormous amounts of work that has gone on this. The answers to questions are beginning to come in. And we can do some reasonable speculation now without fully knowing what the issue is with the different variants that have been identified so far with COVID. In fact, just like throughout the whole thing, when one sees it from the inside, the science and the public health and the policy decisions that are going on, it really has been a remarkable achievement. Of course, it's easy to look at any other piece of it and have things to gripe about and complain about and know, especially with 2020 vision, that things are not perfect. But I must say that I am, as most scientists, a professional skeptic, and it's part of our job is not only creating, but in being skeptical about things and being a destroyer as well as creator, that I have to say I've never been involved in a situation akin to this in terms of people pulling together scientifically and on the policy and the medical side, completely openly, sharing information quickly, coordinating well. I'm not saying that everything is perfect. So we are in this sweet spot. I'm going to tell you the bottom line. You probably already know the bottom line, and then we're going to go into details. The bottom line is that there are variants of COVID around the world. a small number of them in the UK, that have changed in a way that escapes immunity. And it's quite clear that some of them have changed, yeah, as we're going to talk later, a fair amount in terms of how much they have escaped immunity. What we don't know yet is how much this matters, because I can say a fair amount, but we don't have a yardstick yet with which to measure. It's a fair amount in the sense of we can measure in the laboratory escape mutations, escape from sera. What we can't know yet is how much that matters. And the reason why we can't know yet how much it matters, the answer is that it at least matters a little bit. And it probably doesn't matter enormously. And the answer is somewhere between that. And that's why there's a lot of science going on to be trying to judge as quickly as we can how much does it matter. So I'm now going to talk about why we don't know already how much it matters. And the fundamental answer to that is that we don't have enough examples yet of these variants infecting people that have either already been infected or already vaccinated to know whether or not, if we've been exposed to a previous and the most common variants of COVID that we've been exposed to know whether we've been exposed to those or if we've been vaccinated to those, how much risk we face against these variants. And even this question of how much risk there is against these variants is also a question of not risk, well, just quite what risk. Is it risk of infection? Is it risk of severe disease and hospitalization, or risk of death? Right? And these are very important things to know when we are considering the sort of extensive measures that have already been put in place and vaccinations that have been done. Should there be an update of the strain in the vaccine and people revaccinated? So knowing just how much these variants matters, we need to know not whether people can be infected by these variants. Of course they can be infected, but we need to be looking in people who have been infected before to see if they get infected again and how severely, or vaccinated before. And we need to be looking in people who have been vaccinated with the different types of vaccines. And we need to be looking not at those people today in April 2021, but we need to be looking or trying to figure out what those people's immunity is going to be like when they're likely to face these variants, when travel restrictions have been released, or perhaps next winter time, because winter time is a time when most respiratory infections transmit more easily. The parts of the world where these variants, well, firstly, there is one part of the world where we can say something about one of the variants, and that's the variant that was first detected here in the UK. Whether it was origin in the UK or not is a different question, as I'm sure most of you know, but the UK has really excellent surveillance and detailed surveillance of exactly which strains are circulating. And so the UK variant, I will refer to variants by the name of places when they were first identified, but also briefly by their name. So the B117 variant. We do know about this one. And we know about this one, and we know enough about this one to know that the vaccine doesn't need to be updated for this one, because this variant is the predominant variant in the UK, has circulated widely in the UK since around about Christmas time. And in the UK, there is very good tracking and looking for people who have been reinfected. There are extensive cohorts of people who are followed looking for reinfections and for looking at people who might get infected after vaccination. And there's been lots of vaccination already, so there can be studies looking for failures of vaccines. And it's clear from looking there that the UK variant viruses are protected just fine, as you will know from the news, against by prior infection and vaccination. Probably the next most important variant you will have heard, that is the most important variant, and you will have heard of it, is the South Africa variant. And the South Africa variant, well, first identified and mostly circulated in South Africa. This one is clear from laboratory testing in South Africa and also the sharing of those strains in the UK, the United States, and many other countries as well, that the South African variant is different enough to escape immunity to some degree. You might hear me during this talk use the phrase has enough antigenic variation or has changed antigenically. And if I say that, what that means from a technical immunology standpoint is the part of the virus or the phenotype of the virus that is related to how well our immune systems sees the virus. So antigenic difference is what matters for judging to see whether or not strains escape immunity. The South Africa virus, it does change antigenically. It does transmit. There are plenty of people in South Africa that have been infected. It's now in many parts of the world. However, in South Africa, it's not clear whether or not this variant has reinfected people who were infected before with another variant. It's also the case that there was very little vaccination in South Africa, so we also can't tell whether or not this variant, when it circulated in South Africa, was infecting people who had already been vaccinated. So this one is hard to know. We do, however, have a little bit of information on this because there were some clinical trials that were being run on vaccines in South Africa at a time when this is the variant that was circulating. And those vaccines had somewhat reduced efficacy, not enormously reduced efficacy, but a little bit reduced efficacy. One of the vaccines had a much bigger reduced efficacy, but it was a very small study. And so it's hard to really take that information and say, this is how it's really going to be. A couple of other studies that were going on looking at similar variants only showed a little bit of reduction in efficacy. And none of these studies were, the technical term is powered enough, which means from a statistical standpoint, they didn't have enough people in them at different at-risk groups to know whether or not the vaccine efficacy was reduced for severe disease or for death. They were only looking at infections and not, they just didn't have enough numbers in there and enough people who were at risk to be able to see whether or not the vaccine was reduced in how well it protected against people who are at risk. And this is very common for early stage vaccine studies. You can't be testing a vaccine initially in enough people and enough people who are at risk to test for this. And that is the primary thing that we don't know. And the reason why this is such a critical thing to know, firstly, there is the blunt instrument. If we had people who were vaccinated and we're getting infected with variants when we're not protected at all, that we wouldn't need to be looking more carefully to see just how much vaccine efficacy is reduced. But that's not the situation that we're in here. And so we really do need to look more carefully. And we need to look more carefully, being cautious about, as I say, the severity of disease, and also being cautious to take things into account, such as who is being vaccinated. We may be in a situation, for example, that if one is only vaccinating at-risk individuals, then at-risk individuals, yes, they are more likely to die. If they're also more likely to be vaccinated, it's kind of easy to make the mistake that being vaccinated was actually increasing their risk or causing them to die, when in fact, it's because these are at-risk individuals. So there has to be enough data to really sort this out. From a technical standpoint, the thing that we are looking for, the technical term, is that we're looking for a correlate of protection. I remember when I first heard that word many years ago, it wasn't so obvious what it meant. More prosaically, what it means is we're looking for what it is that we can measure in the laboratory after taking a sample from somebody, usually of their blood, but maybe of their saliva or of mucus from their respiratory tract, something that we can measure that in the laboratory would correlate with whether or not they're likely to be protected. Because if we have that, then we can look at how much of that thing people have in the population, people of different ages, people of different times after they were vaccinated, people who were vaccinated with different vaccines or combinations of vaccines. And then we can look in the laboratory at these variant viruses where we know how much that variation would reduce this measurement. And then we will be able to very well estimate how well the population is likely to be protected in advance of an epidemic of such variants. This is something that can be done for most other pathogens, but it takes a little time to establish this. Like with everything, it will be established for COVID probably way faster than it's been established for any pathogen in the past, but it will still take some small number of months yet until we really have that. And however, most likely what can be measured is the amount of so-called neutralizing antibodies in somebody's blood. Now, the virus typically doesn't get into somebody's blood. The virus is infecting our respiratory tract. But if we have antibodies in our respiratory tract, that correlates with having antibodies in our blood. And it's much easier to take somebody's blood and measure than it is to get the sort of stuff out of our respiratory tract that has antibodies in it. And so this is what has been done so far. Even though we don't know what level of neutralizing antibody titers are below the threshold at which somebody can get infected, that is still being worked out by looking for reinfections and looking for vaccine failures, as I mentioned, vaccine breakthroughs. But we can still, and people are in many parts of the developing world, racing very hard and getting serum samples from selections of the population, using serum samples that are already taken, and taking variant viruses and measuring how much those variants drop our current best guess, and probably reasonable guess, of correlative protection. So, is this working? Well, for the UK variant, this has worked well because neutralizing antibodies only drop a small amount. People who've been infected with the original Wuhan variant and then we look at how well, or vaccinated with the original Wuhan variant, if we look how well those individuals' antibodies neutralize the UK variant compared to the original Wuhan variant, it's only a slightly less well against the UK variant. And indeed, we know from the UK studies that I mentioned and studies elsewhere that people who are vaccinated or infected with the original Wuhan are also well protected against the UK variant. What we also know is that the common other variants, the one that currently is the champion in terms of the most escape from immunity, is the South Africa variant that I mentioned so far that has been tested. There are other variants, the P1 variant and the P2 variant, that were originally identified in Brazil. They may have originated somewhere else, but they're originally identified in Brazil. And a small number of other variants that they do escape immunity to a fair degree, but not as much as the South Africa variant. There's probably by now, probably 40 or 50 different studies around the world that have looked at these viruses, especially the South Africa variant, to try to assess how well it escapes those antibodies. And this raises another issue as to why we don't know perfectly yet how well the how bad these mutants are going to be. And that is, how do we measure our guess at the correlative protection in the laboratory? The assays, the laboratory tests to do this, there are multiple different ways. And it oftentimes takes an extended period for a new pathogen to figure this out. In the space of just 2 or 3 months, this has already been figured out for COVID. And there are now good and reliable assays among the many that were possible that can judge these effects. And what we know for the South Africa variant is that somebody's antibody levels against the Wuhan, the original Wuhan that is in the vaccines, and that those of us who have been infected either with that or the UK variant in the UK, that the South Africa variant would drop those antibody levels about 10 times. That's maybe a lot. And I have to say maybe, and this relates back to what I said earlier, we don't know yet what the yardstick is for this virus. If this were an influenza virus and there were variants that dropped titers by 10 times, this would be a fairly common situation for flu. About every 2 or 3 years, we need to update the strains of flu that are in the vaccine. And it's typically about this much of a drop that causes us to update the strain of flu that's in the vaccine, so it will protect against the new variants. So if this were flu, then this 10x drop of the South Africa variant would be enough to update the vaccine. But we don't know yet if it's also enough for COVID. And this relates to the correlative protection. Let's say that somebody has an antibody titer after having been vaccinated, and that titer is 1,000. And by titer, this is just a laboratory technical term for how good those antibodies will react against a particular variant. Let's say that somebody's vaccinated with the Wuhan vaccine, the strain that's in all of the vaccines so far, and they have an antibody level that is 1,000 against Wuhan or against the UK variant. Well, the initial laboratory estimates would say, well, against the South Africa variant, they're only going to have an antibody titer of 100. That's what this 10x drop means when we measure that in the laboratory. Well, that's a big drop, right? I mean, we always listen to orders of magnitude in all aspects of many things. This is where we need to know what the correlative protection is. The correlative protection for neutralizing antibody titers for influenza is around about 40. And so if that is also around about the titer for COVID, then an individual who has an antibody titer of 100 against South Africa, we would still expect to be protected. But we don't know yet where that threshold is for COVID. And this is what I mentioned in the first part of my talk, what needs to be figured out. So this is why we don't know yet, and this is how it's being figured out. The next part that I'm going to talk about, I'm going to talk for about another 10 or 15 minutes before we go to the question and answer section. I've talked about 4 different variants, the UK, the P1 and P2, found at first in Brazil, and then the South Africa variant. You may have heard of other variants too, or variants that have particular amino acid substitutions or combination of substitutions, or deletions of particular amino acids. You may have heard of variants from India, or from Uganda, or from Tanzania and Angola, or from New York, or from California. If you're in this field, you've heard of all of these. And within those variants there that have different amino acid substitutions. This is a completely normal situation. For other infectious diseases, there are also many variants. In fact, for COVID, we probably have a little bit more than we would normally see. And one of the reasons for that, especially now where there's a lot of restriction on international travel, is that if there is a variant that is a lot more fit than other variants that perhaps would sweep the world and take over, that is precisely what the international travel restrictions are trying to inhibit. And so the idea that we might hear this variant there and this variant of the other, we are going to be hearing more of that because of these travels. But it's not, it's not that unusual that even in the flu world, we see many different variants. Well, how much attention should we be paying? And that's the question. There's hundreds of scientists and public health people around the world who are figuring this out in a very collaborative way. I'm part of extensive groups in the UK figuring this out, and extensive groups in the United States. And what we need to figure out is what matters in these variants. One of the things that can happen is that there is, let's say there is a variant that comes up in a particular individual, and that seeds an infection in another individual, and it just happens to take off by chance. But those substitutions are actually not changing the phenotype of the virus at all. They're not changing that it transmits better. They're not changing that it is more pathogenic or that it escapes immunity. They're just part of the random variation of the fact that viruses change. Just like everything changes in nature, and viruses are oftentimes masters of such change. So we have to figure out whether or not these mutations matter. And in some sense, we are a little bit unlucky with COVID in the sense that it has changed antigenically this quickly. We all expected this virus to change. The other 4 coronaviruses that are endemic in humans that most of us have had from when we were kids that typically cause not much more than common cold. These viruses also change in humans. They are not noted for enormous change. None of us have been vaccinated. There are not vaccines against the other 4 coronaviruses that have circulated in humans for as long as we know. But we do know that they change a little. There's not been in the past an enormous amount of work on their change because it's not thought that they change in a way, and the amount of disease that is caused by them has been nowhere near, as far as we know, probably is nowhere near as much as what is caused, for example, by influenza, where there is this global tracking system for these changes. Many of us are vaccinated every year, and as I mentioned, the vaccine of flu is updated on a routine basis. So in some sense, we're a little bit unlucky that the SARS-2 coronavirus is changing antigenically already. In another way, we're very lucky because it seems to be changing in a way that really makes sense from a scientific standpoint. The reason why that is lucky is because the more that we can understand it, the more that rather than just chasing variant after variant after variant that are coming up all over the place, we can try to find general principles about the effects of the individual amino acid substitutions that are causing the changes in the phenotype that are important in these variants. And indeed, the 3 variants that changed the most, as I mentioned, the 2 Brazil variants and the South Africa variant, although those 3 different lineages, those 3 different variants, they emerged and they evolved independently of each other. The key substitution, and they have different substitutions from each other. They have some substitutions in common. And it was very quickly worked out, I think it was probably back in February, just a couple of months after these circulated, that there's one amino acid substitution. It's an E to a K at position 484 in the spike protein of the virus, that has happened in all 3 of those lineages. Now that's a good thing from a scientific standpoint. If the virus were changing antigenically and every time it changed in a different way, that would be a far more difficult situation to understand, and it would be a far more difficult situation to control. Because there is a single amino acid substitution that is in common among all of these variants, that means that it's likely, we don't know for sure, and it needs to be tested, but it's likely that a vaccine against any of them would protect against the others. It's also the case that there are now multiple other lineages that are coming up around the world that have this particular substitution in them as well. And we can know in advance, before that virus can come into a laboratory or be made in a laboratory and tested, that process that takes a few weeks, we can have a very good idea in advance, okay, it's going to be like these other ones. This, from an evolutionary biology standpoint, is called parallel evolution, where something happens in parallel in different places. Another term for it is convergent evolution. To just bring this out of the world of viruses for a moment, the eye, the eye, it looks like from an evolutionary standpoint, has evolved in at least 40 independent different ways in different species on Earth, all to do the same function, to be able for the selective advantage of an organism to be able to see, but to have evolved separately in all those situations. There are other examples of this, like flight, for example. Bats are mammals that fly. Bats are mammals that fly. Completely different evolution of flight from birds that fly, and other species that fly or have partial flight as well, where that has evolved independently. So things make sense. They also make sense from what we know, not only from the broader evolutionary biology standpoint, but also from other pathogens. In influenza virus, my first love, there are also multiple examples like this of parallel evolution. So things are changing. There's lots to be investigated and to be investigated quickly, but prior experience is going to make this happen, or enables this to happen and be made sense of. at an extremely fast rate. There are some other substitutions as well, in particular parts of the spike protein that look like they also cause antigenic change, and that are different from the substitution, the E484K that causes these changes in South Africa and the 2 Brazil variants. The India variant, for example, has a couple of substitutions that are different, some other substitutions that are different. But here again, the science that has been on infectious diseases that has built up over the years puts us in a really great place to be seeing what's happening here. There's a laboratory in the United States that does really excellent work of screening different possible variants of the virus, of many different possible variants of the virus, to assess in a very high throughput way just which substitutions are likely to cause antigenic escape. And they did this work about 2 months ago and published it about 2 months ago. And sure enough, these other variants that are coming up in nature, they are also substitutions that this work in Jesse Bloom's laboratory in the United States, the work is called deep mutational scanning, that they are also something that looks like that this can be predicted. The things that look most likely in that experimental predictive work typically are substitutions that are coming up. The other thing that allows us from an evolutionary biology standpoint and a horizon scanning standpoint to look for what might be coming next is the fantastic amount of sequencing of COVID strains that has gone on. The UK has been a world leader in this, but there's been lots of other sequencing around the world. To give you an idea for scale, influenza viruses are probably the most closely investigated viruses on a routine basis for vaccine update, vaccine strain selection purposes. And there are about 20,000 strains each year that are investigated that are sequenced and are investigated for antigenic change by an absolutely fabulous World Health Organization coordinated system for monitoring variants and updating vaccines. For COVID so far, there are, last time I looked, over 1 million different sequences that have already been done in just a little bit over a year, compared to 20,000 per year for flu. In fact, it's probably substantially more than that right now, because the last time I looked was around about 3.5 weeks ago. And when I looked about 3 weeks before that, it was about 800,000. I say I looked. People in our laboratory here in Cambridge, who are the ones that actually do the great work on this sort of stuff, and in many other laboratories, they are the folks that look and tell me. This gives an opportunity to see. So this gives us an opportunity to see in nature early warning signals of something starting to come up. When we read about variants in the newspapers and the common variants that you will have heard of, and some of the ones that I mentioned before that you may or may not have heard of, those so-called variants of interest or variants of concern, if they look like that they're causing more disease, those are things that we're seeing sort of after they have happened, or after they have already started to happen and come to prevalence to be causing substantial numbers of infections. But oftentimes in nature, there are little signals of something happening here and there. And because of the great depth of sequencing that is happening around the world, and the almost instantaneous sharing of those sequences among all scientists, so that we all have access and people looking at this stuff in many different ways, we can look for these early signals, what people in the intelligence community might call chatter. And if you see it a little bit in one place, okay, we don't have to pay. It might be important, but we probably don't have to, well, we don't have to prioritize looking there immediately. But if something is happening a little bit in multiple places, then this can give us an idea for things that should get into the pipeline of people who are doing these tests to see how much the viruses escape immunity, to get an idea for what we should be watching before epidemics take off or local outbreaks take off with variants. This is a way to get ahead of the game, and there are multiple laboratories. I know the ones in the UK and the US, and also in the Netherlands and in Germany that are starting to do this. And so even while we're still just tracking the common ones, this enormous response, an excellent response that has been to COVID, is already trying to get ahead of the game. There are something like 60 different amino acid substitutions that we and other groups have come together to identify that should be tested this way. In one part of the spike protein, the place where most antibodies are detected, about another 70 in a different part of the spike protein, and then probably about another 30. That is our current list of mutations that should be investigated. And the planning is that these will be characterized in 2 or 3 different major types of the virus. These substitutions will be put in the virus and tested in laboratories in very safe ways to do this. And then when we see these variants, that come up around the world, new variants that are always going to keep on happening, we will be able to estimate very quickly what the phenotypic effect is likely to be. Are they likely to be escaping immunity? Are they likely to be maybe transmitting better or causing more severe disease? Be able to estimate that from this horizon scanning and screening that goes on and get ahead of the game on that too. This is going to be happening, well, just in the next smallish number of weeks, there will be data on all of this. So as I said at the beginning, we're in a sweet spot where we don't know everything, but we know a lot. And I told you here, giving you guesses on what we know so far, told you why we don't know stuff that we would like to, an idea for about how long it'll be before we know that, and how we're trying to get ahead of the game. And we, of course, is hundreds of scientists and people who work in public health around the world. And in my particular case, the we is our sister laboratory in Rotterdam, led by Ron Fouché, and the people in my laboratory here in Cambridge that are working very heavily on this, Sarah James, Eric LeGresley, and Sam Turner, and Barbara Mullerman in Berlin at Charité Hospital in Berlin, one of the expert places for coronavirus research, working there with Terry Jones and with Christian Drosten. Barbara did her PhD here with us in Cambridge and has been very much an enormous part of our team that has been looking into this stuff here. So that's it in terms of my prepared remarks, and it's now time for what I hope will be an even more interesting part, our interaction on this. Over to you, Julian.
Well, thank you very much, Derek. That was utterly fantastic. I was trying to keep up with it in live tweet. There's been a lot of people who couldn't be at it, who also thought it was amazing. And we've had 20-something questions submitted, so we may not be able to get all of them. But I'd quite like to start off with just a few things about how we can go. So firstly, the optimistic questions. Do we think there would ever be a universal vaccine available for SARS-CoV-2 or indeed for influenza? Could we ever come up with something which will work against everything?
Yes, that's a very good point. Everything that I've been talking about now in our current vaccines, of course, they go after that primarily work great against one strain, and then variants of that. And then when the variants become more and more, they start to reduce their efficacy somewhat, and the vaccine strain needs to be updated. It's exactly the same thing for the licensed influenza vaccines. And there is enormous research that has gone on. It has been the holy grail of influenza virus vaccinology for probably 4 decades to make such a universal vaccine. And especially in the last 10 years, there have been tremendous advances and multiple approaches there. Indeed, there are already proposals for this, that for COVID, that leverage work that has been done for other pathogens. In many instances, it has been people who are working on flu. I think absolutely it is possible. Absolutely, we should be investing substantial work on that. They're going to be further away than these strain specific or strain and their neighbors specific vaccines. But yeah, just like we're going to get cures for this cancer and that cancer and that cancer in the future that we didn't have 10 and 20 years ago, we're going to have these vaccines as well, in my opinion.
And a question here from Chris Timmis. Is it possible to develop vaccines that interact with the body of the virus rather than the spike? There's been a couple of questions about that. Why do we target the bit that changes rather than the bit that doesn't change?
Yeah, exactly. And it's exactly the same thing for flu. We typically target the stuff that changes because that's the stuff that our immune system goes after well. And that seems like a little bit of a strange thing to say, and it's a little bit circular. In the case of COVID, our immune system primarily makes neutralizing antibodies against the spike. In the case of flu, it makes neutralizing antibodies against the spike equivalent for flu, the hemagglutinin. The obvious way to make effective vaccines is to mimic a natural infection. And we mimic a natural infection, we could get a good natural immune response against that part of the virus. We can get good immunity, but it's not universal immunity. Now, why do we do that? Yes, we do it because it's the obvious, straightforward thing to do. But we also do it because it's what our immune systems are able to do. And we can't know this for sure, but it's a pretty good guess that the reason why coronaviruses, and COVID is just one example of coronaviruses, the reason why coronaviruses, influenza viruses, other viruses as well, the very fact that they change in these places that our immune systems are really good at going after is because that's the primary place that our immune systems can go after. And so that's the selective pressure for the pathogen to evolve from that. And yes, conserved parts of these pathogens, they do offer the opportunity for universal vaccines. But there's a reason why they can be conserved in nature. It's because our immune system has a really hard time getting there. So the virus doesn't have to change them. And so that's why it's harder to make a universal vaccine than it is to make a vaccine that is more strain specific.
I mean, a question from Neil Bobber here. Could the viruses mutate in such a way that they don't need the spike protein, or do they always have to have some form of spike protein to be targeted?
Almost certainly the coronavirus needs the spike protein. I say almost certainly because this is a new virus and we don't know everything it can do yet. It turns out that it can delete part of its spike protein, and it can delete, I think maybe it's 6 or 8 amino acids in some variants get cut out of the spike protein, and it can still be a spike protein. This is, the spike protein itself has many hundreds of amino acids, so it's only a small part, but it is a part that antibodies can go after. And it may well be that in its original species, before it got into humans, it needed that, but it doesn't need it in humans for some reason. And And this happens with other pathogens as well. For flu, there are some rare cases of flu where not its primary surface protein it can do without, but it can do without its secondary surface protein. It doesn't work so well, but it's possible. But the virus, it needs to be able to get into our cells, and the spike, from everything we know so far, it needs its spike to get into our cells. So it probably can't do without all of its spike. But there's also some indication that it might have two ways to get in, or at least that there are two parts of the spike that are relevant. This is something that's still being worked out. It might be able to lose one of them.
Gosh. Now, there's been lots of questions about relationships between infectivity and severity. So some variants might be more infective but less serious. And so do we know much about this for COVID? Is there a correlation between how infective it is and how severe it is?
Well, again, I'm going to say probably, but we don't know completely yet for COVID. But what we can do is to look at the other pathogens. And COVID is on all of our minds, and it seems particularly scary, but actually it's not that much different from many other pathogens that we face. It's particularly relevant because almost none of us had immunity to it before this pandemic. So we're all exposed, and not exposed like we are to the other coronaviruses as kids. But, some of us have got more gray hair and some of us are less fit and more at risk. And, those people for regular coronaviruses, they got exposed to kids, so they have some immunity. So they're less at risk. Okay, in general, it seems like the less pathogenic a virus is, so the less severe disease it causes, that maybe that makes it transmit more easily in some ways. In what ways? Well, if we have a little bit of a cold, we still might go to work or we still might send our kids to school. The virus has to transmit to be able to be infectious. If we have a really, really bad infection, we can't get to work, or the kids won't go to school, or they won't be accepted in school. And so part of this is who we come in contact with. And the more mild the disease, the more people we're typically going to come in contact with. On the other hand, typically, the more the virus grows within us, the more nasty we're going to feel from having that infection, both from the damage the virus does and from our immune response to the virus. And the more that there is virus in us in general, the more when we breathe or when we sneeze or when we cough, whatever it is for that particular pathogen, the more virus is going to be excreted, the more virus is going to get out and thus can infect somebody else. And so in general, infectiousness has to do with how much virus we excrete and how much contact we have. And so these two things typically trade off against each other. And different viruses have different strategies. Just like if we look in the macro world, different carnivores have different strategies as well. Vultures go after dead meat. Cheetahs run after zebras or whatever they run after. It's the same with different pathogens, and it still has to be worked out all the way for COVID.
Just to say, we're getting questions coming in faster than we can answer them, so we won't get through every question. I will do my best to get through a fair number. You talked a bit about sort of how easily it can spread. There's been a question from Eliane Brachwell and similar questions from a few other people about a relationship between how easily it can spread, which might relate to lockdown measures, for example, and the occurrence of harmful mutations in the virus. Does it get worse, or is it protected from getting worse if we lock down more tightly and hence prevent spread?
Yes, well, viruses adapt, and the primary thing, perhaps the only thing that I talked about in my prepared remarks had to do with escaping vaccines. But yes, the virus will also adapt to change how pathogenic it is, and it will adapt for how transmissible it is, and it will adapt to, yeah, whatever will be selected for and has a selective advantage. This is the sort of stuff that the virus can do. And yeah, if we change behaviors, there is an opportunity for the virus to adapt to those changing behaviors. This stuff is harder to understand and it's harder to figure out. It's harder to work out in the laboratory. The tests for that are just harder to do than these escape tests. The primary focus, the primary immediate focus is, do we need an updated vaccine? And so much of the work that goes on is the question of antigenic change. But there are absolutely laboratories that are looking for this other stuff as well.
And you talk about changing vaccines, and again, there's been a cluster of questions about the new vaccines. So Ian Harvey, just asked, how easy will it be to tweak those current vaccines to address new variants? But also, Eliane Rockwell says, will the Pfizer vaccine that's based on mRNA technology be the easiest, or are basically all the different vaccine types equally easy or hard to update?
Yeah. So there are already phase 2 clinical trials that are going on with the Moderna RNA vaccine with the South Africa variant and combinations of that. So in one arm of that study is the South Africa variant, in another arm of that study is a different dose of the South Africa variant, and in another arm of that study is both the original Wuhan variant and the South Africa variant, a so-called bivalent or two-strain vaccine. There are other trials that are going on. So that study started, I think, about maybe 3.5 weeks ago. And that's being done in people who have been previously vaccinated and also being done in people who are vaccinated for the first time. It's just fantastic how fast this stuff is happening and thoroughly. Other vaccine manufacturers will be doing the same thing or are doing the same thing. And yes, some technologies are going to be easier than others. And again, we leverage here from all the work that was being done in some cases for flu, in other cases for other diseases, to have these different vaccine techs that can be brought so quickly. And as we all know, there are multiple different techs that are licensed already, and many, many more that are being trialed. And some of these, some more changeable than others.
So we've talked a lot about vaccines. Bill Kalogerakis and Jeffrey Vernon, I think a couple of other people have said, but why are we using vaccination rather than, for example, antiviral compounds? We use antivirals for herpes, HIV.
Yep.
Why aren't we using those?
Yeah. There's a couple of reasons. Forget for a moment the beauty of vaccines. The fact that vaccines teach our immune systems how to deal with a particular pathogen. I find that to be just a gorgeous concept, and how to deal with it for an extended period as well. For pathogens that don't change over time, for life, and for pathogens like flu that do change, and COVID, we see how much it continues to change. We can get revaccinated. So there's two things. One is the fact that when we're vaccinated, we are protected for an extended period of time. The second is for respiratory infections that happen in a very acute way. They tend to have a rapid onset. So from the time we start to feel symptoms, it's not very long after that until the viral load in us actually peaks and then starts to come down. In the case of flu, for example, where this stuff is worked out so much better, the actual virus that is in us is typically just there for 4 or 7 days and reaches its peak viral load after just 2 or 3 days. So if we're going to have an antiviral drug against flu, and there are multiple very effective antiviral drugs against flu, we have to take them within, well, what it says on the packet, it says take within the first 24 hours. They're even more effective if you can take them within the first small number of hours, because then you have more chance to nip the infection in the bud. If the peak of viral load is after 2 days and you don't, you go to the doctor after you start to feel bad and you get the drugs, and then you go to the pharmacy and you get them and you take it after a day and a half, you're not going to affect that peak so much. And so the other thing about antiviral drugs is getting them quickly enough for infections that are acute. For situations like HIV, for example, or for herpes, where small molecules are really excellent drugs, this is because these are chronic infections that last for a long time, and we're not faced with get in early, because that's when you really need to get in. These drugs, they can be useful, of course. They can also be useful for people who have longer infections, and it doesn't mean that we shouldn't be taking them for COVID. The earlier we take them, the better, and vaccines give that more breadth, and you can walk around expecting to be more protective rather than waiting to get infected and then treat the infection.
I think it's very helpful. And we've got a question about how the vaccine works. So Kevin Okolako asked about how protective the T cell responses are likely to be.
Yeah. I said at the beginning that this would become more interesting when we got onto all the questions, and thank you everybody for these great questions. Absolutely. We don't know. There are groups that are looking at this. It's harder to look at, which is one of the reasons why it's not known yet. T-cell vaccines, oftentimes going after things that are more conserved, for example, T-cell vaccines or T-cell immunity. This is also one of the ways, or in combination with other ways, to get more universal vaccines. Yeah, it's being worked on, and it's known. It's harder work to do and to figure out. And to give you an example of that, we still barely know for influenza, where T cells have been looked at for decades. We still don't know just how important they are in humans, at different severity of infection, and just how broad the immunity is. And we don't have effective T cell vaccines against flu either. There are plenty of people that are working on it, just like in COVID, but the initial effort has to go to stuff that we know can work more quickly. Other stuff like that, it goes on in parallel, but it takes longer.
Mark Wainwright just pointed out that one of the differences between antivirals and vaccines is that antivirals don't reduce transmission. They don't promote longer immunity in the community. But
absolutely. And we're not going to take them if we're asymptomatic.
Well, so that actually brings me to the question I was about to ask, which particularly comes from Rob Shepherd. Why is there such a difference in immune response? Why are there some people who get very ill and others are asymptomatic? What's going on there?
Yeah, well, that is not my area of expertise, so I can't answer that. But what I can tell you is it's the case for many other pathogens as well. COVID is not special in this regard. And similarly for other pathogens, there's situations where we don't know what's going on. Some of it, of course, is genetic susceptibility. Some of it is for other at-risk things that we know, people who will be prioritized for vaccines. Some of it might be the dose that one received or the particular variant that one got. I know that the person who asked the question asked a sophisticated question and probably knows those things. It's possible that there's more details known about some of this stuff, but in general, it's hard to know.
And we've talked a lot about humans. Jazz asks whether the coronavirus attacks other species and whether that's being monitored. And the question I don't know is there a risk that it becomes a reservoir, that while we can reach herd immunity in a human population, if enough animals carry it, we'll never escape?
Yes, and Jazz probably recognizes that we know that at least minks can get this infection and can get it from humans. There's been instances of this in Denmark and in the Netherlands and in the United States and probably other places that I don't know about. There may well be other species as well. We know that some other species had it that gave it to humans, or that where it transmitted into humans. And again, this is common for other pathogens too. And it's also common that indeed the virus being in other species, these are the reservoirs for other cross-species transmission events. That's absolutely right. Yeah.
Now, there's also...
And I will say one more thing, that there are also coronaviruses, just like there are flu viruses in multiple species, smallpox viruses in multiple species. There are already known, before all of COVID, coronaviruses in multiple other species as well. So different ones are already out there, and this one can get into at least minks quite easily, it seems.
Yeah, I mean, Liz H pointed out that if the cold virus isn't changing much, then it must be able to evade that immunity and continue to spread.
If which virus?
The cold virus. You said earlier, I think it doesn't change much.
Yes, the other coronaviruses that typically just cause common colds, and we get them as kids and then perhaps re-get them a bit as an adult. Yes, they don't change so much. There's not actually been enormous amounts of research in the past of how much they change. So that is happening more now, and we will learn more about those coronaviruses as we discover more about this one, not only because more people focus and to do that comparative work to see how do the others change, to give more of a heads up for how this one will change, but also that the laboratory methods for looking at this coronavirus will help to, in more detail, study those other coronaviruses as well. As I mentioned at the beginning, the laboratory assays to reliably look for antigenic differences, they have had to have been developed and different ones tested. And indeed, the starting point for that has been the research that has happened since, I think it was 2003, when a virus not dissimilar to this coronavirus, which is called the SARS-2 coronavirus, but the original SARS coronavirus that got into humans in Asia and caused problems in Asia in 2003, and a little bit where it got out into other parts of the world. People who have continued to work on that virus in the intervening almost 20 years, that's where these assays have been, were already a little bit available, and methods to make the vaccines effective. There was already a start there, so that work could be taken, and that's why to give more of a running start for this fantastic rapid vaccine response that there's been.
So we're beginning to run out of time, and you've been phenomenal speaking for well over an hour already. I'd like to just have a sort of couple more policy-related questions. So one question, Shivani Singhal asks, what would you suggest is the most effective strategy to combat vaccine fear or the anti-vax movement?
Wow.
Easy questions.
And not just for COVID, but for all of the childhood vaccines, all of the adult vaccines against human papillomavirus. I don't know what we can say, and there are people that really focus this. All I can say is that, even before this, when I look at my own risk, I'm 61 years old. It's not so uncommon, for example, for people to get shingles. I don't know if shingles runs in families, but I've had a couple of family members that have had it and friends, and it's nasty. I, as an adult, a year ago, took the new shingles vaccine as soon as it became on the market. And so all we can say, I think, is, those of us who vote with our feet and all of the work that behavioral people do, study for trying to do this. And, I like to think that if you give people all the information, that they can make good decisions, but I guess that's because I live in a science world. And yeah, I think the other people are better skilled at judging that than I.
We could spend the whole hour and a half on anti-vax and what we need to do. Nina Seeger asked a couple of things, but one is, we have a continuously changing variant picture. We seem to have uncertainty about the levels of vaccination protection. So does that mean we're going to have to continue to yo-yo with lockdowns?
Well, again, that's not my domain to say, but one of the things that we can think about is, again, to look at other pathogens. If we look at influenza, for example, this is the one, I talk about it because it's my first love. It's also the one that in many ways is the most related, because there are influenza pandemics and then what happens? In the last, there's been 4 in the last 100 years, 1918 that killed about 50 to 100 million people worldwide, less severe ones in 57 and 68 and then 2009. Well, what happens after that happens? Well, there is very severe initially, and then the virus becomes what we call endemic in humans. It continues to circulate. People will get reinfected. It doesn't get eradicated. And, it either becomes less pathogenic, or when we've been infected before, subsequent infections are not so severe. And so, we don't continue to act as if there's a pandemic going on, but we get on with things and we take the burden of influenza, and that kills worldwide 500,000 people a year. 500 million people get vaccinated against flu per year. 10% of the world's population gets infected. 1 in about 1,000 gets hospitalized, and as I say, about 500,000 die. It's likely, we don't know, but it's likely that this is what will happen with this coronavirus. It will become endemic. It will continue to circulate in humans. It's possible that it could be eradicated by fabulous new vaccines, but the more likely path is that it will become endemic, that those who are particularly at risk will have to be revaccinated, and there will be a vaccine update strategy. This is what is being planned for, and the sort of horizon scanning work that I talked about is part of all that, and many people are involved in getting ready for this and laying down the foundation. Whether it's needed or not is another thing. Whether it's going to remain sufficiently pathogenic that there will have to be repeated lockdowns, I'm not the one to say this, but that is not what has happened in other pandemic situations like with flu.
So perhaps a final question of all the questions of interest to everybody, but from Rebecca S., who actually asked, should we be allowing international travel this summer?
Yes, I laugh. I know that it's not funny. I mean, there's the pleasure of travel, and then there's the travel to see loved ones in other countries, or, ill-loved ones in other countries. It's not a laughing matter. Again, this is something that needs to be considered at a level where it's a multidisciplinary science and policy discussions for figuring out the trade-offs of this, the trade-offs of restrictions compared to the positives of restrictions. And, this is really something that, my guess on this is as good as anybody else's. So I won't pretend to be an expert on it. Not that I think it's not a critical question. And there are many, many people in many countries that are trying to figure this out.
Well, I mean, we could go on for many hours, but that's been really fantastic, Derek. Thank you so much for spending the time to educate us. I've certainly learned a huge amount. This video will be on in a couple of days' time, so do send it to other people who may have been interested. And if you're interested in the issue about vaccines, then just coming up on the 7th of May, we have a very special event with the Intellectual Forum, where we have the Assistant Director General of the World Health Organization, Dr. Peter Singer, coming to talk about vaccine equity, the defining challenge of our time. Are we getting vaccines to those who need them most as swiftly as we can? So if you'd like to hear from somebody who really is the world expert, or one of the world experts on this issue about vaccine equity, Peter would be amazing. I don't know if have you worked with Peter, Derek?
No, but critical question and very important stuff. It's great that he's coming to talk here.
So we also then have some other events looking at other issues. We always try to have a wide variety of speakers. We're going to be talking about how businesses are organized, from the medieval commons, the organization of modern business. We've got another talk coming up about what should a government be? How should governments innovate? How should they use technology to do a better job? We're going to be hearing from about much more over the next week. So do sign up. Follow our mailing list. You'll see the links in the chat. But Derek, once more, thank you so much for joining us. Enjoy the rest of your evening and good luck helping us both fight off COVID and then back to, I think what you kept saying was your first love. I won't ask whether it loves you as well, defending us against influenza. Thank you very much.
Really my pleasure, and thank you for the invitation and the great questions.